All right, welcome back everyone to Math 107. We are at Lecture 4. And today, of course, we're going to have what I call fun and games. That's graphing techniques. And we're going to be looking at all the objectives on page 266. Let me just flip through here so we can see them. And I basically wrote those out, but I just wanted you to see where they are. We're going to be graphing function using vertical and horizontal shifts and using compressions and stretches and then reflections. Now, because I always think I know better than the textbook, I have a little bit different organization for this. We're going to do everything with the vertical first so that our brains are focused on vertical stretches, vertical compresses, and vertical shifts. And then we're going to do everything with horizontal. And I find that that gives us a little bit better flow. And don't worry, I've already told our textbook author, I think you need to rearrange this section. Okay, so we're going to be working on that today. And of course, we have to remember what we did in the last lecture, our library of functions, because actually our transformation and our graphing techniques, we're just creating new functions from old functions. We're taking those basic functions that we worked with yesterday with those key points, and all we're going to do is just move them around, up and down, left and right, stretch, compress, squash, stretch, whatever, reflect, and we'll just be playing with those. All right, if you're looking ahead in your schedule, you see that very shortly there's a cumulative review section set up. And this is from page 295 in the textbook. And the cumulative review is extremely important because it is constantly sending you back to review your algebra skills. And this is an algebra and trig pre-calculus type course, but we assume that you remember a lot of your pre-calculus, your algebra skills. And so what I want you to be doing, those who are looking by videotape, you want to take this cumulative review very seriously, work it every little detail. It's 2 pages, and I believe if you'll look at your information sheet with the schedule, there's a couple problems left out. I forgot to jot what they were down. Those were not objectives that we required, but you want to write out every problem just like it were a test. And for the people who are here with me, they're going to do that, and I'm going to bring their papers up, and that's how I'm going to try to help correct your math communication skills. We're going to look at it together and sort of say, does this problem get a check plus, perfect, or does it just get a check, or what needs to be done, so that we all learn by mistakes. So do your very best. But I want to reference and remind you that first problem there is just a linear equation, and I'm sure you know how to do that. But problems 2 through 5 are quadratic equations. Okay, well, let's just say that you remember something about quadratic equations, but you need to review it. I would encourage you to go to the table of contents in your book at the very beginning. Where is it? Yeah, right at the beginning. And if you look at chapter 1, if you come down in chapter 1, you will see solving equations, and there's linear and rational expressions. Where do I see solving equations? There's quadratic equations. Oh yeah, equations, excuse me, I couldn't read. I'll blame it that I couldn't see it. Okay, solving linear and rational equations, thank you, not expressions. Quadratic equations. Then quadratic equations when you have complex solutions. And one of the questions, I think I can just flip very easily, number 9 in the cumulative review says solve in the complex number system. So if you forgot about complex numbers, you'll want to go back to the section 1.4, chapter 1.4 at the beginning of your book and look at that. Radical equations, that means when it's got a root. And if you look at problems number 6 and 7, there's a cube root. Number 7 is a fifth root. Those are called radical equations. So you go back and look at that little section. Question 8 has an absolute value in it. That's an absolute value equation. And if you look, I saw absolute value. Section 1.5, here's your absolute value equation. So it looks like much of that first part of the cumulative review is going back to chapter 1, having you review sections 1.2 through 1.5. And I know there's a solving inequalities question in there. So you'll want to refer back, and again, this is an excellent, excellent exercise. Every time there's a cumulative review in the chapters, if you look ahead, you're going to be required to do this, and it's so that once you get into calculus, you are going to be very good, that you will not have forgotten your algebra skills. So work these in great detail. Any questions in here about this? This is due Monday for this class. Okay, everybody good? Alrighty. First thing we want to do before we start our graphing techniques is not look at your work. And we had some functions yesterday that we quickly learned how to recognize. So I'm going to give the function, and everybody's finger in the air is going to do Sesame Street. How's that sound? All right, what does the graph of y equals square root of x look like? Y equals square root of x. Yes, it's that sideways parabola. Give me a point on it. 1, 1. 1. Okay, what's another one?
2, 4.
How about 4, 2?
4, 2.
4, 2. Another one.
16, 4.
Okay, but it starts at 0, 0. 0, 0, 1, 1, 4, 2. Good. All right, fingers in the air. What does y equals x squared look like? Y equals x squared. Okay, that's your good old parabola. Give me a point.
0, 0.
0, 0.
1, 1.
1, 1.
4, 2, 4.
2, 4. Okay, what's another key point? Go the other direction.
Negative 2, 4.
Negative 2, 4. That's good. Or I was hunting for negative 1, positive 1. Usually when we're in this class, our key point is negative 1, 1, 0, 0, 1, 1. Okay, what about y equals 1 over x? That's called our reciprocal function. Yep. Let's see if I can do this backwards. Here we go. Right, right. Okay, yeah. It has asymptotes, the x and the y-axis. Key points are 1, 1 and negative 1, negative 1. Good. All right. What about y equals x cubed? Y equals x cubed. Yeah, you're right. That part looks like a parabola on this side of the y-axis, and then this part looks like a downward parabola. What's some key points? That middle one is 0, 0. When you come over this way, what was another one? 1, 1. And going down the other way? Negative 1, 1. Okay, those are great. All right, how about, y equals cube root of x? That's the S one that everybody has helped me learn. Okay, that's the S one. And your key points there, again, are pretty easy. The 0, 0, 1, 1, negative 1, negative 1. Oh, what's the absolute value of x look like? Okay, that's our V. That's our V. We got two straight lines coming in, intersecting at 0, 0. Okay, was that it? I believe that was it, wasn't it? Good. All right, so what we're going to do today is play. We're going to take those basic ones and we're going to shift them, stretch, compress. And unlike the order in the book, we're going to do everything vertical first, and then we'll come back and do horizontal. All right. So we're going to play with y equals x squared, because if we understand how to shift, we're going to start out with shifting horizontally. Our first goal is horizontal. That's a R. Whoops. Horizontal shifts. Oh, you're right. I meant vertical. Okay. Thanks. Keep me straight. Vertical. We're going to work with vertical directions. Woo. And we're going to start out with the shifts. All right. This is how I remember it, and everybody has their own silly ways of remembering things, so whatever it takes, do it. But for me, when I think vertical, I think up and down, just like this. Okay, when I'm thinking up and down, and I'm thinking of a coordinate system, am I thinking x values or y values? Y values. Okay, so when I think vertical, that is going to have effects on y values. Right? Vertical, up and down. All right. So we're going to start out, and I drew this on Maple. I have the graph of y equals x squared. So I'm going to call this f of x equals x squared. Now all I want to do is take our good old basic function, and I want to do a vertical shift. I just want to go up or down, vertically up or down. So I ran this off. This is called high tech here. Okay, so here is y equals x squared, the same old graph, and I just want to shift it up and not change its shape at all, or shift it down. If I do that, my x values are staying the very same, but my y values are going up or my y values are going down. Do you see? All right, so this is in this fun and games. So here we're creating a new function and we're going to shift up, for example. So we're going to start out with my function f of x equals x squared. And I am going to create a new function that is called h of x. I'm going to create a new function h of x by shifting my f of x. So I'm going to take good old f of x and I'm going to shift it up 4 units. So here's really still the coordinate system down here, and all I've done is increase my y values by 4. So h of x then will be my old function, and I'm adding 4 to it. Do you see? I'm taking my old function and adding 4. Well, that old function happened to be an x squared. So my new function is x squared plus 4. Now, keep in mind that that vertical shift affects the y values. It only affects the y because we're going up and down. So on the graph of y equals x squared plus 4, I'm going to keep my same old x at 0 and my x's at 1. All right? I'm just going right back to my good old basic function, which is 0, 0, 1, 2, 3. Is that a... Okay. 1, 1, and negative 1, 1. All right, so I'm going to keep those same values. All right, now, remember on the old it was 0, 0, 1, 1, and negative 1, 1. This is the old y equals x squared. If I'm affecting the y values, to get my new graph, all I'm doing is adding 4 to the old y's. Do you see that? So really, my y values now to get y equals x squared plus 4, which is my new h of x, I'm just going to go add 4 to the y values. So the new points will be 0, 4, 0, 5, 1, 5, and negative 1, 5. So I'm shifting up 4, 1, 2, 3, 4, and what I like to do is just put in a little axis, like this is my new x-axis. And now I'm just going to plot the graph y equals x squared. So I come over 1, up 1. I go to the left 1 and up 1. And here's my good old graph y equals x squared, 0, 0, up 1 over 1, to the left 1, up 1. But really, I've taken the whole thing and shifted it up, so this point is 0, 4. This point is 1, 5. And this point is negative 1, 5. Pretty easy, huh? Okay. So basically, for a shift up, your new function is just going to be your old function plus you're adding on to the y values. All right, let me see what you can do. I want you to, the words on a test would say something like this. Use transformations. These are called transformations. To sketch the graph of y equals the square root of x minus 3. Identify 3 key points. We'll do this one together just to make sure we're all here. Okay, we're going to use transformations to sketch the graph of y equals the square root of x minus 3. Okay. Try to be good with your units. Okay. All right, so we're going to analyze this and we're going to know exactly what we're going to do. What is the basic library function that we studied last time that looks like that's in this new function? What's the basic function you've already learned? Square root of x. So we're going to look at f of x equals square root of x. Okay, so that's step 1. So our basic square root of x, everybody knows that's 0, 0, 1, 1, and 4, 2. 4, 2, 1, 1, 0, 0. This is y equals square root of x. Okay, now what we notice is that we have this new function where y is equal to our basic function, and then we're going to subtract 3. Remember, f of x gives you a y value, y's from the old function, and then we are subtracting 3. Okay, so if we just even follow that, we had the point 0, 0. So if we're going to subtract 3 from that, the next point should be 0 minus 3, because we're going to subtract 3 from the y's. We had the point 1, 1. So if you subtract 3 from that y value, you'll have 1, negative 2. And we had the point 4, 2. And if we subtract 3 from the 2, we will have 4, negative 1. Right? Isn't that what we're expecting? Because it's only affecting the y values. All right. Now, when I'm using words, this means I'm going to use my basic function square root of x, and I notice that the y values are going to be decreased by 3. So that means I'm just basically shifting down. That's called shifting. I'm going to shift down 3 units. So my basic function is just being shifted down 3 units. So what I like to do, everybody can do like they want to. Once I do this little shift, I just go in there and pretend like this is my coordinate system. Put in like, my brain's going 0, 0, over 1 up 1, over 4 up 2. It's just like I'm sketching the graph of y equals the square root of x, but I just shifted it down. And look at there, it's exactly the points we found, 0, negative 3, 1, negative 2, 4, negative 1. Do you see how that works? Who wants to ask me a question? Are you good? Everybody got it? All right, so it's your old function, and then you're either adding or subtracting a number to it. That's called a vertical shift. Vertical y values. Okay, next topic. Vertical stretches. Vertical stretches. Okay, and compressions. Okay, vertical stretches and compressions. All right, when you hear vertical, you are thinking what? Y values. All right, so I hate to be this, but I'm a little parabola. We're in Sesame Street. All right, if you think vertically stretch my arms, what am I going to do if you stretch my arms? Right? Okay, that's a vertical stretch. All right, here's my arms, I'm the parabola. And you're going to compress my arms. What are you going to do? You put weights on them, right? Okay, so here's your parabola. If we stretch vertically, you're going to pull me up like this. If you compress me vertically, those are y values. You're putting weights on my arms and bringing them down. Okay? All right, vertical Remember, you're thinking y values. So you're only affecting your y values. Stretch, you're pulling up and making skinny. Compressing, you're flattening out because you're putting weights on it. Okay? Now, how does that work? All right, so we have some function y equals f of x. This is one of your basic functions, basic. Okay? So to stretch, if you're keeping your x values the same, and all of a sudden your x values are the same, but your graph is going up faster, aren't you multiplying those y values by a bigger number? You've still got the same x, and instead of it going here, it's got to go way up here. So to stretch it, you will take your basic function and multiply by number a, where a is greater than 1. So you might be saying 2 times your y value, or 3 times your y value, or 4 times your y value. You're making it bigger. Now, what do you bet happens when you want to compress your function? It's going to be the, well, you could write it as a times f of x, where a is a fraction between 0 and 1. Like you're going to be half the y value, a fourth of the y value, because you normally would come up 1, but now you're only going to come up a fourth of the way. Some people would say, okay, if a is bigger than 1, always you could just write it as 1 over a, and I think that might be what you just said. So the idea is that if you put a fraction between 0 and 1, your y value is not going to go up as far, it's just going to go up a fraction as far. Everybody got it? Okay, so let's have some fun. All right, remember stretching, we're vertical, so it affects y. Vertical is y. Stretching, those y values got to get up faster, so you're going to multiply by a big number. You want to compress, you want your y values to drop down, you're going to have to multiply those by a fraction between 0 and 1. Okay, here we go. All right, we want to, okay, this is, we're still vertical. It's very important you keep up with, because in a minute we're going to do horizontal, so vertical. So we know that means y values. So the only thing that's affected are the y values. And we're going to do a vertical stretch. Okay? All right, so we want to, the instructions are use transformations to sketch the graph of. All right, everybody got it? Use transformations. We want to sketch, say, h of x equals x squared, whoops, forgot to put the number in front, 3x squared. Okay? We want to sketch h of x equals 3 times the x squared. All right. Let's don't forget what our basic function is. Basic. What's our basic function? Y equals, it's your parabola x squared. So let's just draw it so we can see how it's going to fit on here. And try to spread out the units a little bit so that it'll be clear. Okay, so the first thing I'm going to do is just plot y equals x squared, which you can do with your eyes closed, I bet. It's like this. Okay, and I'm just going to put over here the numbers -1, 1, 0, 0, 1, 1. And you could go ahead and put in 2, 4, all those if you want to. All right, now for h of x, these are the old y values, and they're going, because x squared is your old y, right? And you're going to multiply your old y values by 3. So I'm going to keep the same, this is for 3x squared. All right, so I keep the same old x's. And now the y values, the y values are going to be multiplied times 3. So instead of a 1, it's now going to be 3. Instead of 0, 0 times 3 is still 0. So we still have 0. And this one is also going to be 3. Okay, so only the y values are affected because x squared really is my y. So I'm multiplying 3 times that y value. So we have 0, 0. We have 1, 3. And we have negative 1, 3. I think I just said those backwards. Negative 1, 3 and 1, 3. And the graph has the same old x values. But it's like you took my arms here and you pulled them up. You stretched them up. Does everybody see that? It's 3 times the old y values where y is x squared. All right, while we're on the same page, does anybody need me to slow down a second? Let's sketch g of x equals 1/2 x squared. Okay, and I'm going to go ahead and pull this out to negative 2, 4 and 2, 4. So I have a few more points to play with. Okay. Alrighty. Now we want 1/2 times our old y values. And I keep repeating the same thing, but I'm hoping by the time you take a test, you hear me saying this to you on the test. I'm going to take my old y values and multiply times 1/2. Everybody see it? Alright, so I still have the same old x values, which would be negative 1, 0, 1. Now I'm going to go negative 2 and positive 2. Alright, I'm going to look at my old y values. My old y values are 1, so now 1 times 1/2 is 1/2. My old y value is 0, 0 times 1/2, still 0. 1 times 1/2 is 1/2. 4 times 1/2 is 2. 4 times 1/2 is 2. I'm only working with my y values because it's 1/2 times the y. Everybody got it? All right. So we now have the point negative 1/2. This is like we got weights on my arm. 0, 0, 1, 1/2. And then I took it out a little further. Negative 2, 2. And positive 2, 2. And here is compressing. Words are compressing. Compressed my function. All right? Are you an expert? All right, let's put it all together and make sure you are. You need me to hold that there just a second? Question?
G of x.
Right here? This is...
We can't see.
Oh, I'm sorry. Thank you. This is my new function I just graphed. G of x equals 1/2 x squared. Thank you. You guys are so good at helping me. And I do seriously appreciate it. All right, everybody good? All right, here's fun and games. Give me what function you want to play with, not a line. That's too easy. Which one of your basic functions you want to play with?
Cube.
Cube. All right. So we want to use transformations, or also called graphing techniques, to sketch the graph of h of x equals, you want to help me? Let's don't make it too hard. How about 2x cubed minus 4? 2x cubed minus 4. Is everybody good? So let's list our little steps here. let's say what's going to happen. We're going to analyze the graph, and I actually just made up the test for this particular class. Doesn't mean it's on the video people's test, because I change test every semester. But I just made up your test, and you had to use words to talk about the transformation before you actually made it. So that way you get your thoughts together. So let's get our words together. Words. All right. What is my basic function that I'm using? Y equals x cubed. Okay? Now, what does the 2 in front of the x cubed tell me we're going to do? We're going to stretch what direction? Up is called vertical. So we have a vertical stretch. By a factor means multiplication. We have a vertical stretch by a factor of 2. Okay, now what does this little -4 right here tell you you're going to do? Shift down vertically, shift down. Vertical, shift, I'll use all your words, down 4. Okay, so we have analyzed this graph. We know it looks like a y equals x cubed. We know we're going to vertically stretch it by a factor of 2, and then we're going to drop it down 4. Everybody good? All right, so let's do our transformations on here. And I think on your test I said you have to use a half a sheet of paper. Yes?
Which one will we do first?
Question is which one you do first. What I'm going to try to do is always do it one way in here, not to confuse you, but it really doesn't matter. And your book, I'm trying to follow the way your book did it, which is not the way I always did it. They like to do the stretching and the compressing first and then do the shifting. And then they give you an example in there that says, but you didn't really have to do it in this order. So to prevent any kind of confusion, I'm going to always try to do the vertical stretching and compressing first before I do the shifts. But that's not the way I did it for 20-some years. But anyway, so to answer your question is you really don't have to do it in a particular order. As long as you start out with your basic. All right, so I'm just going to flip the page over so I make sure I have plenty of room. And let's set up our graph. We know we're going to be shifting down 4, so you might as well put a lot of space below the x-axis. Okay? All right. Put away your calculator, no fair. Y equals x cubed. Let's put that in first. Everybody knows that's 0, 0, 1, 1, negative 1, negative 1. And the graph looks like this. This is y equals x cubed. Okay, and your test question says identify key points and keep up with them. So let's keep up with our key points here. All right. The next thing it says vertical stretch by a factor of 2. So am I going to worry about the x values at all for a vertical stretch? No. So all I'm going to do now is go in here and multiply my y values by a factor of 2. Right? Y values times 2. So 0 times 2 is 0. 1 times 2 is 2, but I keep my same x value. So I have now 1, 2, because 1 times 2 is 2. And then I have negative 1, negative 2, because I multiplied this negative 1 by negative 2. And you'd really see the stretch more if we even went to 2 because it was 2, 8, and then if you multiply the 8 times 2, you got 16, so it really pulled it up. You see that? All right, so here is, whoops, there's my stretch. Remember, I'm stretching vertically, so it's getting closer to the y-axis. So this is y equals 2x cubed. Okay? All right, what's the next part? Shift down 4. So all I'm going to do is try to pick that thing up and drop it down 4. So what I like to do is kind of draw little axes across here. And I'm going to just pick this thing up and move it down. And really your y values are being decreased by 4. Remember, a shift down, the y values are being decreased by 4. So you're just pulling 4 off the y values.
So okay, use the y value that you got from the multiplication.
Right.
Okay.
So I'm going to subtract 4 from this. So I got 0, negative 4. Subtract 4 from your 2. So I'll have the point 1, negative 2. And subtract 4 from that negative 2, so I'll have negative 1, negative 6. Subtract 4 from that y value because a vertical shift says you're shifting down 4, you're bringing 4 off this y value that's right here that you've already built. Does that make sense?
Not the original?
If you did your stretching first, you're not off your original. It's 4 that's coming off this thing. See, we graphed that thing, 2x cubed, and then we pulled off 4.
What about the other one?
The other one didn't have a, when we did the earlier problem, it didn't have a stretch on it. That one right there didn't have a stretch on it before I did it. And then that one didn't have a stretch. But once we did a stretch, we only did the stretching part, and now I put the stretching and the shifting together. Is that good? Everybody good? All right, let's do one more so everybody feels great. But let me show you this, just make sure you're good. So here is the graph of h of x equals 2x cubed. That was green, subtract 4. So the blue is the x cubed. The green graph is the 2x cubed, and then the red is the whole thing. Does everybody see how it's built? All right, one more, and then we're going to get on horizontals quickly. All right, so that's, shall we do you want to do a square root? Okay. Yeah. Okay, you want to use graphing techniques, or transformations or whatever to graph h of x equals 3 square roots of x plus 2. All right, take a second and write out the words, what's going to happen here. Discuss it with your neighbor if you'd like. Write out the words. All right, what would you tell me on a test? What would be the first thing in words? Basic function
Vertical offset.
is y equals square root of x.
That shifts up to.
Yes.
On the test, are you going to look for us to write all the words out like that?
When I I think I think the test I made out for you, this particular class, this semester that's in here, is I did say use words to describe, then
Yeah.
sketch the graph.
Because like when I just take my notes, because I know how the what the wording is. I just like jot down. I put basic, square root of x, stretch 3, shift 2.
Okay, you probably need to get the word vertical in there because we're going to have horizontal shifts in a minute, and horizontal stretches and horizontal compresses. So be sure you're focused that we're on the vertical. You want to be as specific as you can. Yes.
You would never do a vertical and a horizontal at the same time, would you?
Oh yeah.
You would?
And that's really going to be fun. His question was, would we ever do vertical and horizontals at the same time? Yep, we're building on that and looking forward to it. You are looking forward to it, right? Okay. All righty. We're starting at the bottom and we're working our way up. All right. Now, what is this 3 going to do? Vertical, stretch. You are good by factor of 3. For those who are watching this by video, this is Friday, and I'm just giving all these people here something to entertain their guests with over the weekend. You can teach them all about stretching vertically and horizontally. This is in case you're bored Saturday night, you know? Or how to get rid of your friend that's near you, I guess. You could start talking math. Okay, what's that plus 2 going to do? It's a vertical shift up 2 units. Okay, everybody got it graphed? Great. Hand me yours and I'll put it on the screen.
It's not very neat. I guess I should label my answer. Oh well, my pencil's not working.
All right, I'm just going to show you this real fast. How much credit you think this is going to get on a 10-point question?
Not very much.
Not very much. You haven't labeled your axes, you haven't indicated your units, you haven't identified your points, and personally I can't see what's going on in here.
Terrible.
Terrible? I'm going to let you write that on his paper.
I can see it not.
I'd be sued for hurting his ego. All right.
Might have to.
Okay, everybody graphing? Ooh. Y equals square root of x. About to put y equals x squared. All right, I know everybody's got that one. Okay, now we're going to do a vertical stretch by a factor of 3, which just means all the y values. Factor means multiply. We're going to multiply all the y values by 3. So 1, 3. And 2 times 3 is 6. 6. Oops. So this is y equals 3 times the square root of x. All the old y values are multiplied by 3. Is that good?
Now, when we're doing a graph, do you want us to also include the regular function too?
You have to be very careful what the instructions say. If it says graph each transformation, then you would.
So you'd have to put.
Part of doing this is to try to force you to start analyzing graphs, saying things, visualize, communicating that I know that I'm just multiplying these by 3. I know I'm shifting it vertically to try to make you practice what you're saying. Just like if you had to give a speech on what a great person you are, you wouldn't just stand up and say, I'm great. You have to say, what made me great? Okay? How was that for an example? All right, the next one we're going to shift up by 2. That means all these y values from here, 3 square roots of x, are going to be shifted up 2. So, whoops, I didn't want to use black. I used green. It's going to shift up vertically everything by 2. So all in green now, all the y values, I'm just going to add 2 to, because you'll see it's like I have this y value and now I'm adding 2 to it. So 0 plus 2 is 2, so I have 0, 2. At x equal to 1, I'm going to add 2 to the 3, so I have 1, 5. I'm just adding 2 to the y values. I keep the same x value 4, and I'm going to add 2 to the y value. 6 plus 2 is 8. So I have 4, 8. I just added 2 to these y values to come up with y equals 3 square roots of x, and then I added 2 to it. So all of these values just add 2 to the y values. Am I perfect?
What's that line for?
That's to help me know, because I've done this so long, this is the way my brain works. I just saw that I was going up my function is going to be shifted up 2 units.
Do we have to do that?
No, you don't have to do that. I'm sorry. That was the way somebody taught me a long time ago, and no, you don't have to do that. All right, everybody good on that? Perfect? All right. We are now experts in verticals. Now we're going to go to horizontals. Horizontals. Okay, and the first thing, horizontal. Remember, vertical was up and down, y values. All right, which way is horizontal? Left and right, left and right. What kind of values are those? X values. Horizontal shifts. These are X values. It says, play with the X's, leave my Y's alone. Okay, we're only playing with the X's. All right, now, the horizontals, the reason I do them second is because they always seem backwards from what you expect. They always seem the opposite of what you expect. So I don't know how to tell you to remember when something's horizontal, it's just going to seem totally backwards. But I'll show you how it works. Here is y equals x squared. And if I want to shift it horizontally to the right, I think that number's a 4 there, it's hard to see. 4 units. Horizontally just means I move the same old graph over 4 units.
On the x-axis.
I only affected the x values. I still have the same old y values that went with it. So I'm affecting the domain. So what I have to do to shift this to the right 4 units, remember I just told you it sounded backwards. If f of x is x squared, if I want to come up with shifting it to the right for h of x is going to have to be my f of x, but I'm affecting the domain. And that is going to be x minus 4. And the way I remember this is when x is 0, x squared is 0. But over here, if my x is 4, that is the only way I'm going to get that value there to be 0. So to shift the problem that I just showed you over, it's going to be x minus 4 squared. So it affects the x's. This says I'm really decreasing my domain by 4. That's what it says. But if you have a decreased domain by 4, you had to go the other direction to get to the 4. So this is the graph. This in black now is the graph of h of x, which is x minus 4 squared. Notice that if you let x be 0, the y value is 0. If you let x be 1, you come over 1. You've just been shifted over by 1. If you come over to the right 1, which then is going to put you at x at 5, you're at 4. If you go over 1, remember you go over 1 up 1. If you went over from 1 from 4, you're at 5. 5 minus 4 is 1. 1 squared is 1. If you go to the left 1, you're over at 3. I'm going to draw this in just a second. 3 minus 4 is negative 1. Negative 1 squared, positive 1. So it's just going to be that same graph shifted over. All right, let me just draw it. All right, this is going to be, when you have x minus 4, it's going to be a shift to the right 4 units. It's called a horizontal shift. Horizontal shift. Okay? Now you're going to see why I put that little dotted line in, by the way. All I'm going to do is come over, it's like I'm shifting over the y-axis 4 units. And then you just graph your little graph, 0, 0, 1, 1, negative 1, 1. It's like you're graphing y equals x squared. But your points really are 5, 1, 4, 0, 3, 1. And let's see if I can do it with the original points. When you had x squared, you had negative 1, 1, 0, 0, 1, 1. So now when you do x minus 4 squared, it's going the opposite direction. I don't know how to tell you this except you're going the opposite direction, so you're really having to add 4 to the x values. So when you add 4, because that's really what made this part come out to be 0, when you add 4 to the x part, you will get 3, 1. I'm really adding 4. When you add 4 to 0, you get 4, 0. And when I add 4 to 1, I get 5, 1. And you can double check those. You see that those points actually work there. Okay? So for horizontal shifts and stretches and compressing, horizontal is the weird one. It's going to end up being basically the opposite of what you think it's going to be. Okay? Because it's affecting the domains. All right? So just think horizontal, weird, opposite. All right, let me give you one to graph. Let's go to y equals square root of x. Okay, let's graph h of x equals the square root of x plus 2. And let's use those words and get this. How do you know this is not a vertical shift? It's not added on to this, it's part of the domain. You're right, it's like f of x equals square root of x. Now if I find f of x plus 2, that's my new h of x. Remember how you evaluated functions f of x plus 2? It means where there's an x here, you put a x plus 2. Okay, so see how it's affecting your domain? All right, so we would say our basic function is y equals square root of x. What's our shift? It's horizontal. And which way are we going? Horizontal, left, 2. It's a horizontal shift of left 2. A negative 2 in for x is going to make that equal to 0. Now your book doesn't mention this, but really if you start thinking about the domain, what's your domain here? What's the domain of this function?
Everything except for 2.
Remember what's underneath the radical?
0, nothing.
Has to be greater than or equal to 0. X has to be greater than or equal to negative 2. So that sort of tells you right there where your shift's gone when you think about what your domain is. All right, let's see if we can sketch this. All right, we'll start out with square root of x, 0, 0, 1, 1. 4, 2. Y equals square root of x. Okay. Now we're going to take this and we're going to play with the domain, and this is going to be a horizontal shift to the left of 2. So what does that mean I'm going to do to all these x values? Subtract 2. So I'm subtracting 2 from all the x values because it's a horizontal left 2. That's a negative direction. I'm going in the negative direction 2 units. So we'll come over here. So now my point is negative 2, 0. My point is negative 1, 1. And my point is 2, 2. 2, 2. Okay, and this is y equals the square root of x plus 2. Oops, forgot to write the point down. That's 2, 2. Okay? All right, so all I did was pick this up, move it to the left 2 units. Everybody good? All right. What comes after horizontal shifts? Stretching and compressing. All righty, let's get a visual on this. Here is my function. If I tell you to compress my arm, what are you going to do? Pull it in, right? You're pulling it in. It's affecting the x value. You're pulling it closer to the y-axis. Okay? Now, if this is my arm and I tell you to stretch it, what are you going to do? You're going to pull it out of socket, right? You're going to pull it out further that way. Okay? So stretching horizontally is this way. Compressing horizontally is pulling it in this way. This is the y-axis right here. All right, so let's get our little formula, and then we're going to pick up with that in the next lecture. Okay, so horizontal, stretch, and horizontal compress. Okay, now the interesting thing is with anything to do horizontal and x is opposite of what you think. Opposite of what you think. So if you have a stretch, if you have f of x equals f, maybe I should call that a y. Y equals f of a times x. The a is in here multiplied times the x this time. It's not on the outside. Remember, that was vertical. F of a times x. Your domain is being affected. Okay. When a is bigger than 0, you think a being bigger than 1. When a is bigger than 1, you're thinking, that must be making it bigger. But see, what you've done is really cut your domain in half. So that will be compressed by a factor of 1 over a. So if this is like finding f of 3x, it's going to shrink it in by 1/3. Opposite, reciprocal of what you think. The stretching, whenever a is between 0 and 1, such as a half, what happens is you've already cut your domain in here. So when you have a like a half, by the time you put it in there, it's going to stretch it out. It's going to stretch it out. Okay, horizontal is the weird one. It always looks opposite of what you think. So your shifts are opposite. If it's x plus 2, you're going to the left. If it's x plus 3, you're going to the right. X plus 2. X minus 3, you're going to the right. If you have 4x as your domain, that's going to be a compression by a factor of a half. If it's 1/4 x, it's going to be a stretch of 4. And that's where we're going to start the next part of the lecture. So take a break and get ready for the next part. Okay? You will be hearing it on the video. Alrighty, welcome everybody back. We're at Lecture 4B. I had hoped to finish the curve sketching in Lecture 4, but did not. We left off with horizontal stretches and compresses. We had looked at horizontal shifts. And when we're horizontal, we're thinking in terms of axes. And the thing I told you to remember, it always seems backwards from what you think, the reverse of what you think. So we're going to pick up with the stretches and the compresses. And then easy is reflecting about an x-axis, not too hard, reflecting about a y-axis, and then we'll have our functions all built. Then, very, very important for calculus is section 2.8. All this is important, but 2.8, I've actually even brought in the calculus book that if you're here at State, you'll be using to show you how you're going to be seeing it right in your calculus book. We're going to do the basics in here, which is set up the functions. In calculus, you will then go a step further for like in your optimization problems. So this is a very pre-calculus topic, and we have to do it. All right, so we're on horizontal stretches and compressions. Just quickly review for horizontal. When we did a shift, it's either to the left or to the right, and our brain is thinking x values. We're leaving our y's alone. We're just working with our x values. So if we were going to graph something like h of x equals x minus 3 cubed, that looks, this is just review, in case you can't tell, review. We did that last class. All right, this looks a whole lot like the function y equals x cubed. And because it's inside parentheses, the x minus 3 here, I should have used a different number. Let's make that an 8. X minus 8 cubed, so we don't have so many 3's here. X minus 8. Give me the words to tell me what we're going to do to this graph to graph h of x. Shift, which way? To the right, how many units?
8.
Yeah, I changed it to an 8. So this will be a shift this way, that's called right, horizontally, 8 units. So the only values you're going to change in your -1, -1 points, your 0, 0, and your 1, 1, remember those are the points here, you're going to go to these x values, because we're only working with the 8s, and we're going to go to the right, that's a plus, we're going to add 8 to those x values. So you'd have 8 plus -1, which is 7. You add 8 to 0, so we have 8, 0, and we add 8 to 1, and we get 9, 1. Okay, so we've just taken all of our x values and added 8. Okay, everybody good with that? If we were going to sketch that graph. All right, we did that last part near the end. All right, so now we're focusing on our stretching and our compressing. Horizontal, and let's do a horizontal stretch first. Oops, I can't spell. The problem is we were talking about milkshakes before we started, and I'm having a sugar craving. My brain's not working. Stretch, horizontal stretch. Sorry about that. All right, so you have y is equal to some function. If we want to stretch, if you remember from the last class period, I told you it's going to just be the opposite of what you think. To stretch it, this a has to be some number between 0 and 1. So we'll take the problem y equals 1/2 x squared. Okay, this is the function we're going to look at. Y equals 1/2 x squared. Okay. All right, let's draw the coordinate system and let's put good old x square in there to start with. And we'll see how we're going to affect it. And then we'll just double check our points and you'll see that it works. All right, so we would say that this is our basic function, y equals x squared. And then because this is 1/2 times the x within the quantity that's being squared, it's not 1/2 then the x squared, it's the quantity 1/2 that's then squared. We're going to stretch, and this will be horizontally, by a factor of what? 2. Okay, that's the weird part. It's always the reciprocal. The factor is the reciprocal of what's right there. All right, but I'm going to plug the points in and show you that that's true. All right, so let's first graph y equals x squared. And so we'll put 1 right here, 2, 3, -1, -2. 1, 2, 3, 4. Okay, remember horizontal is just playing around with the x's. We're going to leave our y's alone when we work with it. So good old y equals x squared is 0, 0, 1, 1, -1, 1, and let's put in a 2, 4, and a -2, 4. So here is y equals x squared. Okay? Now, if we're stretching it, it's like we're taking it like this and we are pulling it horizontally. Pulling it horizontally. Okay? All right. Let me label the points so we'll see the numbers. 0, 0, 1, 1, 2, 4. -1, 1, -2, 4. All right, remember you're only affecting the x values. So we're going to take the x values and multiply by a factor of 2. Leave your y alone. So now we're going to have 2, 1. Do you see how I've pulled this over? I've stretched it. Okay, we'll multiply 0 times 2, that's still 0. We're going to multiply 2 times 2, because we're multiplying by a factor of 2. 2 times 2 is 4. So now I will have the point 4, 4. I pull this over. I'm pulling it horizontally. So I'm stretching it out. I've stretched it this direction. Stretch. Okay, over here the y value is multiplied by 2, so that will be -2, 1. I'm stretching this direction, stretching from the ends. And -2 times 2 is -4, that's way over here. This is -4, 4. And so I've just, so I've taken my parabola and I've pulled it out horizontally. Does that make sense, everybody? All right, so your point should be, are you sure you did that right, Ms. McCollum? I really want you to verify that that's correct. So, this is the graph of y equals 1/2 x squared. So let's just check. If x is 2, 1/2 of 2 is 1, 1 squared is 1. There's the y value. If x is 4, 1/2 of 4 is 2, 2 squared is 4. My points check. Everybody got it? Everybody got it? All right, let me give you one to do that. So compression, yes?
Isn't that just like a vertical compression though?
Okay,
With the
all right, that is a very good thing to say because that did cross my mind. If you were looking at this and you didn't have the equation, this looks like a compression vertically. But a compression vertically from the formula appearance, I mean, the appearance looks the same. But the formula for a vertical compression would have to be, can you see this? you need the a in front of the f of x, the y value. So yeah, really, you could come up with a formula to make that look like a compression, but because I only affected the x value inside the parentheses, it became a horizontal. It affected the domain.
I was just thinking, unless, like, if you didn't show us the formula, it was just the graph.
Right. Yeah, if you
Wouldn't
just
know.
saw the picture, it would be hard for you to determine, was I doing a vertical compression or a horizontal stretching. That is totally true. And one of the main things we're trying to do is, given the graph, analyze from the function. Thank you very much. Very wonderful comment to make. Anybody else? And every one of you were thinking that too, right? Y'all need a milkshake also. All right, let me give you a problem to do.
Milkshakes again.
What?
So why are we talking about milkshakes again?
Y'all are the ones that are interested in having a little sugar fix. All right, use transformations to sketch the graph of y equals the square root of 4x. Oh, 4 is too bad because that's easy to do. Try 5. That was too easy. Y equals square root of 5x. Okay, because I do have another topic to do, I'm going to kind of push you on this. Our basic function is y equals square root of x, because we're doing the square root with the x underneath. Is that what everybody was thinking? And now, because we have that 5 times the x, this is grouped with the x, it's going to have an effect on the domain. So it is going to be, it's always opposite of what you see. So it's a compression by a factor of what? You are so good, 1/5. Okay, so our x values will be multiplied by 1/5. You are very good. So let's graph square root of x, 0, 0, 1, 1, 4, 2. 0, 0, 1, 1, 4, 2. Okay, so now we're going to take these x values and multiply by 1/5. So 0 times 1/5 is still 0. 1 times 1/5, right here is 1/5 exactly. All right, so this is going to come over 1 times a fifth. See how we're compressing it towards the y-axis? We're squishing it in. So now we're going to have the point 1/5, 1. It's going to go this way by a factor of a fifth. Okay, this 4 we will also multiply by 1/5, which is 4/5. So that's going to really squish this in. 4/5 is way over here. Oops, that's lining up supposedly with the 2. So now we have the point 4/5, 2. So it's taking this thing and it's squishing it in, compressing it towards the y-axis. And your thought is, if I just saw the graph, it's going to look like a vertical stretch. I know you're thinking that. And it does if you just saw the picture, but the way the function is written, it is taking this graph and it's compressing it towards the y-axis. All right, let's just do, yeah.
Then how could you ever use vertical and horizontal together then?
I'm going to show you in just a minute. All right, let's just double check these points just to confirm, when x is equal to 0, the y value is 0. So that's on the red, 0, 0. When x is equal to 1/5, x is equal to 1/5, 5 times a fifth is 1, square root of 1 is 1. 4/5. When x is 4/5, 5 times 4/5, and then we got a square root. The 5's divide out, the square root of 4 is 2, and there you have it right there. Okay? Everybody good? All right, now let's put it all together. Oh, do I have another pad? Ran out of paper? I know y'all think that means it must be time to quit, but it's not. All right, so we're going to the blue. Oh, do you have a pad? Great.
I guess it was with your stuff, so
Okay.
it's probably yours.
Thank you very much. See, you would be so unhappy if I let you out early because you would say, I'm not getting my money's worth.
I would.
You would. All righty. Let's sketch a graph. Let's put it together. Let's sketch y equals. All right, let's don't go too hard. Let's do like 2 square roots of x minus 3 plus 1. How's that sound? Okay, I mean, we could make some really difficult problems. We're not trying to really make real hard ones here.
Is the plus one
Are you
in the
gonna do
radical or
hard
not?
ones on the test?
I'm going to be fair. His question was, are you putting these really hard ones on the test? If I usually try to make it so that you're showing me you understand the various concepts. The whole idea here really is, can you analyze the graph and tell what's going on?
The plus one's not under the radical.
The plus one's not under the radical. Let's make a list of the things that are going on here. First of all, what's my basic?
Square root.
Y'all are good at that. All right, and we're going to follow the book's lead and always talk about compressing and stretching as the next part. Okay, so what do you think in terms of compressing and stretching is going to happen? It's going to be vertical because there's a 2 right there. So it's going to be a vertical stretch by 2. And that basically is going to give me a 2 square roots of x. If I'm building on my function right here. All right, what's the third thing?
Shifting.
Okay, we're going to go into shifting. And it really doesn't matter which one you do first. Which one do you want to do first? Vertical? Okay, vertical, shift, up, 1. So that's going to really basically give me 2 square roots of x plus 1 if I'm like building my function. Is everybody good? All right, and then what's the fourth thing that's going to happen here? Okay, horizontal, shift. Is that going to be a left or a right? Whenever you're working on horizontals, it's the opposite of what you think, and there's a minus 3. So you're going to go to the right 3. Okay, right is plus, left is minus. Okay, so it's the opposite of what you see. So that will give me 2 square roots of x minus 3 plus the 1. Okay, so that's our pattern. We're going to do all that. We'll have the graph. We'll keep up with 3 key points. 3 key points. And when we have our 3 key points, we'll just double check them. You never want to be so confident in yourself that you forget to double check your points. I'm going to draw this on blue so I don't have to keep flipping the pages. All right, here we go. Stretch by 2. I was just trying to decide where I need to draw my x-axis so that I make sure I have plenty of room here. I think it's going to be okay like this. Okay, so we're going to start out with square root of x, 0, 0, 1, 1, 2, 3, 4, 2, right here. Okay, 0, 0, 1, 1, 4, 2. The next part, we're going to do a vertical stretch by 2. What does that mean I do? What am I going to multiply by 2? The y values. Okay, so the y values are going to come in here and be multiplied by 2. So 0 times 2 is 0. 1 times 2 is 2. Remember, you're leaving your x's alone. And 2 times 2 is 4, so I'm now going to have the 0.44. So this is y equals 2 times square root of x. Is that good, everybody? The y values were multiplied by 2. Okay. Vertical shift up. Vertical, we think y. We're taking y's up by 1. Shift up 1. So what do I do to this? I'm going to add 1 to the y values. So add 1 to 0. So that's 0, 1. I'm going to add 1 to the 2. So now I have 1, 3. And I'm going to add 1 to the 4, and now I have 4, 5. So this is y equals 2 square roots of x, but I've added 1 to that. Is that good? Okay, and the next thing we're going to do is, the key word is horizontal. We're going to do a shift to the right of 3. So if I'm doing horizontal, what am I playing with? Which values? The x values. So now the x values I'm going to add 3 to. The x values I'm adding 3 to. The x values I'm adding 3 to. Very carefully I'm adding 3 to. All right, so I'm going to do this in green, hoping that you're not too colorblind. 3 plus 0 is 3, 3, 1. So I've got 1, 2, 3, 3, 1. That's moving this over to right here. The next one is going to be 4, 3. 4, 3, 4, 3, 4, 3. I'm just moving this one over, 4, 3. And then it's going to be 7, 5. 7, 5. 4, 3, and 3, 1. And this is the graph of y equals 2 times the square root of x minus 3 plus 1. And I've kept up with my 3 key points. Wasn't that fun? All right, let's double check though, because we never want to be so cocky to think we're hadn't made a little mistake somewhere. All right, let's put a 3 in for x. 3 minus 3 is 0. 2 times 0, 0, 0 plus 1 is 1. Check. Let's check the point 4, 3. 4 minus 3 is 1. 2 times 1 is 2. 2 plus 1 is 3. 4, 3. Check. Let's put a 7 in. 7 minus 3 is 4. Square root of 4 is 2. 2 times 2 is 4. 4 plus 1 is 5. Check. We are perfect. Okay? Wasn't that fun? That was fun. Alrighty. I need to quickly talk to you about reflections about the x and reflections about the y. You have lots of these to play with in your homework. write out what you're doing step by step, and you can graph some very interesting looking problems as long as you analyze the graph carefully and go step by step. And enjoy doing it. Enjoy doing it. Okay, the next little topic is reflect about x-axis. And we're going to go back with my illustration here, y equals x squared. If I'm going to reflect something about the x-axis, it's just like I'm going to fold the paper along the x-axis. Just fold the paper along the x-axis, and didn't that reflect it? All right, so to start with, I had y equals x squared. All my y values are positive. If I reflect it, I still have the same old x values, but what happened to the y values? They're the negative of it. You could really get away with that on your vertical stretching and compressing, because instead of multiplying like 3 times it, you just multiply it times -1. So instead of, if your point was 1, 1, 1, 1, if you multiply, instead of multiplying by 3 to stretch it, multiply it by -1, and your y value now becomes -1. See how it's the same thing? Okay, but basically, to reflect about the x-axis, you're just going to say the y values now are the negative of what they were to begin with. It's just going to be a minus in front of your function. So when we had y equals x squared, if you want to look at y equals minus x squared, here's your basic function, y equals x squared, but now all the y values are going to be negative. That sends it below the x-axis. That makes sense, doesn't it? That wouldn't be too hard. Just in case, let's do one real fast. Suppose you were asked to graph y equals minus the square root of x. Your basic function is y equals square root of x, 0, 0, 1, 1, 4, 2. That's y equals square root of x. This negative in front, that's still like a vertical stretch or compress. It just means that your old y values for here are now the negative. You're only changing your y values. So you still have 0, 0, and the opposite, the negative sign of that is 0. This was the point 1, 1. So really it's still like multiplying -1 times +1. I don't spend a whole lot of time on reflecting, because if you've already learned to stretch and compress, you've got it made. If you can understand, I might go in a negative direction. 1 times -1 is -1. So you now have the point 1, -1. I meant to do that in red for the negative part. And here you had the point 4, 2. So it really is like multiplying that 2 times -1. -1 times 2, and you've got your point 4, -2. 4, -2. And here is the graph of y equals minus the square root of x. That is a reflection about the x-axis, but all that's happened is your y values were the negative sign. Or you can say y times that -1, and you're still okay, like the stretching and compressing. Okay, everybody good? All right, so that is the reflection about the x. You would do it when you're doing your graphing, do that at the same time as when you do your stretching and compressing vertically. All right, about the y-axis. Reflection about y-axis. Okay, reflection about the y. This is when you're going to have your function y equals f evaluated at minus x. Okay, what's happening is you're really switching your x's around. If you're reflecting, this one's a bad one to tell, because if I reflect it, it's going to look like the same curve. But reflecting means that I'm going to switch the x values but keep the y's the same, and reflecting means you're going to flip it over. And in this one, when you flipped it over, they just matched on top of each other. But if it was a square root of x, you flip it over, so you're changing your x values. You're doing the opposite of your other x values. Do you see that? So here's the example. You want to, let's pick something that's going to be easy to see. Y equals minus x, but we're going to cube it. Y equals minus x, and then we're going to cube it. So our basic is going to be basic y equals x cubed. Then we're going to, because the domain here, we're flipping the x values in our domain, that's in our domain part. We're going to reflect about y-axis. Okay? So here we go. Great. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, negative 8. Okay. All right. The first thing I'm going to do is graph the basic y equals x cubed. 0, 0, 1, 1, and 2, 8. So we'll have a better picture of what it looks like. And negative 1, negative 1, negative 2, negative 8, like this. So that's 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Okay? All right, so if we have a reflection about the y, this is y equals x squared. Cubed, y equals x cubed. To go to minus x cubed, it just means that we're switching to the opposite sign the x values, but leave the y alone. Okay, so this x value is 1, but we're going to switch to the opposite of that. So we will have negative 1, but leave your y alone. 2, 8, we're going to have the negative sign of the x, so that would be negative 2, 8. We're just flipping it over. Do you see how if I folded it on the y-axis, this is going to come across over here? It's like you're folding across the y-axis. Okay, now the opposite of negative 1, or negative 1 is positive 1. So this one's coming over here. This is 1, negative 1. And the negative, negative 2, the minus the negative 2 is positive 2. So this is going to be 2, negative 8. So this one's coming over to here. And the graph's going to go like this. If you had your sheet of paper and you folded along the y-axis and held it up to the light, you will see that it was that same graph flipped across the y-axis. Flipped across. And that was because it affected the x values there. All right? Okay, you have lots of homework problems to enjoy and practice, and I'm going to back up in a couple of lectures and get some homework questions and let us get caught up, but I need to press forward into the next exercises. Okay, so with the curve sketching, enjoy, take your time though, be very careful, and everything will work out beautifully. All right, let's move on into the next section of our textbook, which is very important. And we are in math models, construct and analyze functions. We're in section 2.8. I'm on page 278. Constructing a function means we're going to give you some words. The authors of your textbooks are not using the words word problems. They're using the words like models, construct, so that you'll feel very positive about what you're doing. So we're going to construct some functions, and we're just going to analyze it and see what information we have about that. Now this is an extremely, extremely important topic that you want to master, because this is one of the major applications in calculus for optimization. We're going to learn to do the algebra part here. Then when you get into calculus, you're going to go one step further. So what I actually did, because if you're in this class, you're not going into the engineering calculus, but you're going into the business and liberal arts calculus, I brought in our current Math 131 textbook for you to see. This is Math 131, Calculus and its Applications. And right in Chapter 2 is where you're going to start needing the material from your textbook, Section 2.8. And the two types of functions that you're going to be studying in 2.8 are where you have geometrical figures like rectangles and circles, rectangles and circles. And I'm showing you this out of the calculus book because they did a good job showing it to you here. And then also when we have boxes and cylinders. So you've had these formulas from calculus before, from your algebra before, but let's look at them and make sure you're good at these formulas, because once you get in your calculus course, you got to review these quickly to be able to work your problems. Okay, just reminding you that when you have a rectangle, the area of the rectangle, everybody just memorize length times width, area of a rectangle, length times width, x times y in this case. Remember, perimeter means add up around the outside. So you have 2 lengths plus 2 widths, 2x plus 2y. Okay, let's jump over to the circle, because these are our geometric figures first. When you had a circle, what your area of a circle is, pi r squared. Pi r squared, r is your radius. Circumference really is just a perimeter, right? Around the outside of your circle, the formula for your circumference of a circle, 2 pi r. Remember these good old things from geometry? Okay, those are your geometric figures, and when you look in your textbook at section 2.8, you're going to have some problems that involve geometric figures, and we're going to have some of those also. Okay, then for these things are called conic sections. Conic sections, this is a cylinder. This is called a right circular cylinder. Well, let's go to the box first. You got a box here. The volume of a box, that anything that goes straight up, you just get the area of the bottom and then multiply times the height. So the area of the bottom's a rectangle, x times y, and in this case the height is z. So you've always memorized the volume of a box, length times width times height. That's just the area of the bottom times the height. Same thing when you have a cylinder here, this is called a right circular cylinder. The bottom of your box is just a circle, of your can, your cylinder. The area of that is pi r squared, that's the area of that circle, and then you just multiply it times the height. So it's easy to memorize the formula for the volume of a cylinder is because you're just taking the area of the bottom and multiplying times the height. Okay? All right, so our job is going to be given a problem, and we have to come up with the function that describes the problem. And they're going to be geometric figures or these kinds of solids. So before I jump on some calculus problems, because I want to motivate you that you need these, I want to just show you these in your textbook. This is in your textbook on section 2.8. The first one involves the area of a rectangle with a fixed perimeter. I'm not going to use the problems in the book because I want to use your other problems and you'll have these to practice with. Okay, the second example is a very calculus related, called the demand equation. And I just want to show you, it is right here in your calculus book that you will be working with next semester. The demand equation. This is in the Math 131 and it's also in your 121, but this just happens to be out of your calculus book. The demand equation for a certain commodity is. And so then you have to do some work with it, but you're going to see it again. I'm just trying to let you know this is extremely important for success in calculus. So we're going to work also with the demand equations, but you also are going to have box problems. Let me go to the applications here. Where do I see the box? Demand. I'm at the here they are. 2.8 at the very beginning. Volume of a cylinder, and you're supposed to do some information with it. I didn't mention the cone to you. They tell you the formula for that. Your third question has to do with the demand equation. We're going to discuss that in just a minute. Your seventh question in the exercises is about rectangular fields. Okay, all of these are the basis for getting into your calculus course. All right, so what I decided to do for our problems is actually pull my Math 131 sheet that I give my students so that you know if you're in 131 you're going to see these kind of questions again, and I'll have to read them to you. All right, what we're going to do is, and so your problems are going to be geometric figures that you need to know, the volumes of these solids, and then the demand equation. So there are three things you need to know how to do out of this section. Everybody got those three things? There's more things than that in your textbook section. Geometry figures, the box and the cylinder, and the demand equation. The three things. All right, so I'm going to do examples of those three things so that you'll be on top of it. All righty, I'm going to have to read this to you. I'm not sure how much you can see. All right, we have a rancher who has chickens. This is a chicken rancher. This rancher has 100 feet of chicken wire to make a chicken yard. One side of the yard will be formed by the side of a barn, so no wire will be needed. Okay, the question becomes, what are the dimensions of the yard if it is to be rectangular in shape? And of course, if you have these chickens, you want to maximize the area for those chickens so they have more space to run around in. So if you just blindly went out there with 100 feet of fencing and put it up, you may not be using your space efficiently. You want to know really what should those dimensions be so that your chickens have more area to run around in. Does that make sense? Just like if you're doing a garden plot, you want as much area as possible. Okay, well in this course and in your textbook, you're not answering the questions, what is the maximum area and stuff like that. It is just asking you to set up the function that defines this problem. Then in calculus, you'll learn to take derivatives to come up with the answer. Okay, so here, all we're going to do is come up with the function that describes the problem. All right? So let's see what we remember about this. We have 100 feet of fencing. That's an F. We have 100 feet of fencing. And what we noticed is that we have a barn. Here's the barn. Draw figures. That helps. It's cold. They got the heat going for the chickens. Okay. We're going to use fencing around the outside so we can put our little chickens in here. Here's the chickens. They're wandering around out there. All right. So we want to put fencing all along here. Okay? All right. So this is, we'll just call this length and width. So if I want to use all 100 feet of fencing, what is my formula going to be that describes that 100 feet?
2W plus L.
Okay, exactly. I have 100 feet that's going to fit right here. Is that correct? So I would say 100 has to equal a W plus a L plus a W, or 100 equals 2W plus L. All right. Now that is what is called a constraint equation. That's called a constraint equation. My question though, if we go back, is this farmer or rancher is very interested in getting as much area as he can for his little chickens. So what we want to do is write a function, and we'll just pick W. We want to write the function area in terms of the width W. Okay, when you go to calculus, what it's going to do, you want to be able to maximize the area. So we want to come up with a formula for the area of this rectangle, but we only want it expressed in terms of the width W. All right, so let's just start out with what we already know. If I have this rectangle, what is the formula for this rectangle? The formula for the area of this rectangle, everybody? Length times width. Okay, but it's telling me I want it only in terms of W. So that means where I have the L there, I need to find a way to express L only in terms of W. So take your eyeballs and go back up here. These are your eyeballs looking over there. And how can I redefine L in terms of W? L is 100 minus 2W. Okay, so I'm going to bring that back down here, and we have 100 minus 2W times W. So the question in your textbook is express the area as a function of the width for this particular situation. And you can leave it like that or multiply it out, and then you get a big old check. So I've expressed the area of this chicken yard in terms of W. In calculus, you learn to take the derivative to find out what maximizes the width, what the width and length need to be to maximize it. Alrighty? Okay, I am behind where I need to be, so Monday we have to finish section 2.8. We're going to do the cumulative review and hopefully start 3.1. Alrighty? Is that good? So you guys have a great weekend.